Okay, welcome back everyone. In this segment, we're going to start talking about the one-dimensional equations of motion. So we've talked a little bit about how to describe motion using graphs and how to calculate some basic things, including derivatives of motion functions. And we're going to start putting this together. So we're going to be looking at this second one in detail. How do we solve problems involving straight line motion that have constant acceleration? And before we do that, we'll take one more example of how to calculate velocity and acceleration as a function of time. So just as review, we said that velocity was the derivative of position. So the derivative of 1.5 will be 0. And it's helpful to write this as negative 4.2 t to the minus 2. And I like to do that because then I can see that it's just going to give me 8.4 t to the minus 3. And then plus 5, because that's 5t to the 1, that turns into 5t to the 0. So that's just 8.4 over t cubed plus 5. Then we want to find the instantaneous acceleration. Well, first as a function of time, so that's dv dt, and it's easier to use this form. So now I'll have negative 25.2 t to the minus 4th plus 0. So remember that this is 5t to the 0, so 0 times 5, when I bring that down, will give me 0. So this is negative 25.2 over t to the 4th. Okay, so we want to find the instantaneous velocity and acceleration at 2 seconds. Okay, so what we would do is we would just plug in that v of 2 seconds, it's another way to write it, is just going to be 8.4 over 8, which is 2 cubed, plus 5. So whatever that number is, we can just pop that into our calculator. And then acceleration at 2 seconds is going to be equal to negative 25.2 over 16, which is going to be 2 to the 4th power. And if we assume that everything is in correct units, this will be meters per second, and then meters per second squared. Okay, now many of you have studied physics before, and if you did, you probably studied the kinematic equations of motion. And so here they are. V equals V initial plus AT, X equals X initial plus V initial t plus 1/2 AT squared, and V squared equals V initial squared plus 2A delta X. And I like to call that the forgotten equation. So make sure you don't forget about that one. Now, where do these come from? Well, if we have constant acceleration, then we can write velocity versus time as a graph that looks like this. It starts at v0 and then just increases with a constant slope. So constant slope translates into a constant acceleration, because that's what the slope of velocity versus time is. And as a matter of fact, this is just the equation of y equals b plus mx. So it's a linear function. Okay, the intercept is v0 or v initial. The slope m is the acceleration a, and time is the x coordinate. Likewise, if we take this graph and we think about what this would translate to in x versus t, it would have to be an upwards opening parabola. And this parabola would be given by the equation x equals x0 plus v0 t plus 1/2 AT squared. Now it turns out that you can also get back and forth from x and v, and we'll talk about that in just a moment. But the final equation on here, the forgotten equation, this is useful if the time is not given. There's no time in that forgotten equation. Okay, so we're going to show how to get that first kinematic equation from the second. So in other words, x is equal to x naught plus v naught t plus 1/2 a t squared. And then v is equal to dx dt, so that's going to give me 0 plus v naught, and then plus at, 2 times 1/2, and then at to the 1. Okay, now we also want to do the second problem on here, which is namely, given a constant acceleration of a, derive the first two. And in order to do this, we're going to start up here and we're going to say that a of t is equal to a, but that's equal to dv dt. And so we're actually going to work our way backwards. Okay, so that means that dv is equal to a dt. And we're actually going to do the opposite or the inverse operation of the derivative, which is the integral. So we'll be talking more about that later, but basically with respect to time, the integral of dv can go from 0 to some later value of v, and we'll say dv prime so we're not messing up our variables. So this would just be v prime evaluated from 0 to v, and that's also going to be equal to the integral from 0 to t of a dt prime, so 0 to t, and actually I evaluated that, didn't I? So that would be a t prime evaluated from 0 to t, so that's equal to at. Okay, so basically we could have that v of t is equal to at plus v naught, some constant. Okay, or perhaps a better way to do this is not to evaluate with any limits, but to take the limits away. And I'll try and get rid of that. And so when we do this, we'll get basically v plus c, c1 perhaps, is equal to at plus c2. Now c1 and c2 can be combined. We did two indefinite integrals, so v is equal to at plus v naught, where v naught is c2 minus c1. It doesn't really matter what those numbers are. Now if this is all very mysterious, then you're going to want to go back and review how to do integrals. Wherever you have the resources for that. And we also want to keep in mind that in general, if we have a function f of t is equal to k t to the n, then the integral of f of t dt is going to be t to the n plus 1 divided by n plus 1. All times k plus a constant of integration. Now the reason that you get a constant of integration is that if you take the derivative of a constant you get 0, so we have to make room for that in our function. So if we do that, for example for our velocity function, we say that f of t, which is actually v of t, is equal to at plus v naught. So that means that x of t is the integral of v of t dt. So we have the integral of at plus v naught dt. So we use our rule here. At is going to turn into 1/2 at squared. V naught is going to turn into v naught t. And then we're going to have a constant which we will call x naught. And if you compare this with what we had on the previous page, this is x of t. Okay. So now let's draw some graphs for a particle which is stationary. Okay? So we'll start with acceleration. Well, it's not going anywhere, so acceleration better be 0. And it's got no velocity, so v of t is 0. Okay? And that means that essentially what we're going to have here is that x of t is just going to equal x naught. And the way that we can think about this is that x of t is going to be x naught plus v naught t plus 1/2 a t squared, and both v naught and a are 0. So that's where that comes from. And v of t is equal to v naught plus at, and both of those are 0. So that's where these expressions are coming from. So x is just equal to this initial value of x naught. Okay, what if we have a constant non-zero velocity? So a constant non-zero velocity, we'll call that v naught. Okay, so v of t is equal to v naught plus at. But we might notice that if it's a constant velocity, then that means that the slope, which is the acceleration, is 0. So that's where v of t will just become v naught. Then we have a of t, which will be 0. And finally, x of t will be x naught plus v naught t plus 1/2 at squared. And those are both, whoops, my bad. That first term is 0, so we have x naught right here plus v naught t. So the slope of this is going to be v naught. Okay. Now, let's do one more, and let's say that we have constant non-zero acceleration. So now a is equal to k, some constant. Okay, we could call it a naught if you want, and that means that v of t is going to be equal to v naught plus a naught t. So here is v naught, and it will be increasing like this with the slope of a naught. And then this is actually going to be a parabola, and this will be x of t equals x naught plus v naught t plus 1/2 a naught t squared. And this will be x naught right here. Now earlier in the class, we said that if we had concave up, then that automatically means that we're going to have positive acceleration. And now you can see why. Because here we have concave up, and if you take the second derivative of that, the first derivative will give you the velocity, and the second derivative will give you acceleration, which is just a positive constant value. Now if we had concave down, okay, this would be something where it's like negative 1/2 at squared. Then the derivative of that would be something that looks like this, where we have v naught minus at, and this would give us just negative a for our acceleration. So it's important to keep those in mind. Okay, let's do a couple of quick example problems, and we'll wrap this up. So we have a body moving with uniform acceleration, and it has a velocity of 12 centimeters per second in the positive x direction at the moment that its x-coordinate is 3. If the x-coordinate 2 seconds later is 5, what is the magnitude of the acceleration? So we know that x final is equal to x initial plus v naught t plus 1/2 a t squared. Now t for this is going to be 2, and -5 is going to be x final, and 12 is going to be v initial, and 3 is going to be x initial. So part of doing these problems is just identifying what each of these mean. So then we plug it in, and what we have here is -5 centimeters is equal to 3 centimeters plus 12 centimeters per second times t plus 1/2 a, which is what we're looking for, times 2 seconds quantity squared. You solve that for your acceleration, and you get that a has a magnitude of 16 centimeters per second squared. Okay, basically you're going to get -8, and then you're going to subtract 24 from that, and then you have to divide it by 1/2 times 4, so divide it by 2. So it'll be 32 divided by 2, and then you take the absolute value of that. Okay, so I'm just plugging in the numbers here. All right, one more example. A jet plane lands with a speed of 100 meters per second, and it can accelerate at a rate of -5 meters per second squared as it comes to a halt. What's the minimum time it needs after it touches down before it comes to rest? And can it land at a small airport that has a runway of 0.8 kilometers? So why don't you go ahead and pause and see what you can work out on your own, and then I'll show you how to do this. Okay, so we know that v final is equal to v initial plus acceleration times time. V final better be 0 if it's stopping, and v initial is 100, and the acceleration is -5 meters per second squared, and then t. Okay, so this t here is just 20 seconds. So can it land at a small tropical airport where the runway is 0.8 kilometers long? Well, there's a couple ways to do this. The easiest way is to use the forgotten equation. So v final squared is v initial squared plus 2a delta x. And so delta x is going to be 0.8 kilometers, and a is what we had previously. V final will be 0, and v initial will be 100. And then we'll just have -5. And we're going to solve this for x, and we're going to see whether or not it's less than or equal to 0.8. And when we do this, we get a delta x, which is basically 10,000 divided by 10. X is 1,000 meters, which is 1 kilometer. So no, it cannot land at that airport, which is a bummer. Okay, so that's the basics of using the kinematic equations. And next time we'll wrap up this unit by talking about how to apply those equations to free fall.